Welcome to the Deep Dive. We're the show where we take these really complex topics and try to unpack them, so you can quickly get to the heart of what actually matters. And today, wow, we're tackling something that powers just an astonishing amount of our digital world. But it often operates completely unseen, almost like a silent guardian. I'm talking about the inner workings of an Oracle database.
It really is everywhere, isn't it? Even when you don't realize it.
Exactly. Think about your day. Seriously. Every time you buy something online or you transfer money, check your bank balance maybe.
Booking a flight, interacting with big company systems.
Right, like your company's HR or inventory management. There's a really good chance an Oracle database is just humming away in the background, tirelessly working.
Making it all seem instant and crucially reliable. It's the engine room for so many critical operations.
But have you ever stopped, really stopped, to wonder how this incredibly robust, enterprise-grade system actually manages all that information?
It's definitely not just files sitting quietly on a hard drive, that's for sure.
No, it's way more complex.
Yeah.
There's this sophisticated, almost, magical orchestration happening under the surface.
Absolutely. It's designed to make sure your data is processed quickly, retrieved efficiently, and maybe most importantly, kept absolutely safe.
Safe even if, the power goes out or the system crashes.
Especially then. That's where the real design brilliance shines through, ensuring safety against unexpected failures.
Okay, let's unpack this then. Because you've heard of Oracle, everyone's heard of Oracle. But do you really know what's truly going on behind the scenes? Like how it uses your computer's memory? And what about those essential background operations that actually bring it to life? That's our mission today.
We're taking that deep dive.
Exactly, into Oracle's core architecture. We're focusing specifically on how it uses your computer's short-term memory, the RAM, and those critical processes that make it all function.
And this isn't just theory, right? It's about understanding the absolute foundation, how your applications actually talk to their data.
And maybe why things sometimes feel lightning fast and other times,
Boo.
well, frustratingly slow.
Understanding this gives you that aha moment about performance.
Yeah, it's kind of a shortcut, isn't it, to being genuinely well-informed about a critical piece of modern infrastructure, something that touches almost everything we do online.
And what's truly fascinating, I think, is how meticulously Oracle orchestrates all this. The memory, the processes, it's all geared towards ensuring both incredible speed and unshakable data integrity.
Like a balancing act.
Precisely. It's really a masterclass in system design. Every single component, every process has this precise interconnected role, all working together to maintain consistency and availability even when things go wrong unexpectedly.
Wow. Okay. It sounds like a system built from the ground up to be, what, resilient?
That's the perfect word, resilient.
So where do we start? Maybe the big picture. How does memory even get allocated on a typical server?
Good starting point, because like you said, a powerhouse like Oracle almost never has the machine all to itself, does it?
It has to share the playground.
Right. Exactly. You've hit on a fundamental point about server architecture. Let's imagine you have a pretty beefy enterprise server. Maybe it's equipped with, say, 16 gigabytes of RAM, a decent amount.
Okay, 16 gigs.
Now, Oracle is critical, no doubt, but you simply can't dedicate all of that memory just to the database. Doesn't work that way.
Why not? What else needs it?
Well, first off, you need to install an operating system, right? Windows, Linux, maybe some flavor of Unix. And that OS needs a significant chunk of RAM just to function, to manage the server's basic operations, network connections, disk I/O, all that stuff.
Makes sense. The OS needs its space.
Then, on top of the OS, you install your Oracle database. That needs its slice, but wait, there's more. You might also have a major business application running on the same server.
Like SAP, you mentioned earlier.
Exactly like SAP, or some other big enterprise application. And that application will also demand its own dedicated memory space. It's a busy machine.
So in that scenario, our 16 GB machine, how does that RAM actually get divvied up, practically speaking? What does that landscape look like?
Okay, well, a common, pretty sensible breakdown might look something like this. You could allocate maybe around 4 gigabytes just for the operating system itself. That's its workspace.
4 GB for the OS. Got it.
Then you dedicate, say, 6 gigabytes specifically for your Oracle database. That's Oracle's operational playground, its main memory zone.
6 GB for Oracle. Okay.
Yeah.
That leaves 6 GB.
Right. And for a heavy hitter like SAP, you might also assign that remaining 6 gigabytes. So if you add that up, 4 GB for the OS, 6 GB for Oracle, 6 GB for SAP.
That's our 16 GB. Perfectly allocated.
Exactly. And the really critical takeaway here for our deep dive today is this. Oracle doesn't just greedily grab all the RAM. It carves out its dedicated portion. It has to coexist.
Right.
And our focus today, it's squarely on understanding what happens within that 6 gigabytes Oracle claimed for itself. It's a highly optimized, very carefully managed space.
That makes perfect sense. Like a shared office building, you said. Each tenant gets their floor space, but they all operate within the building's limits.
Great analogy.
So it sounds like Oracle's entire architecture, really at its core, boils down to how it uses and occupies that specific chunk of physical memory, that RAM.
Precisely. The very essence of Oracle's architecture lies in its sophisticated, almost microscopic management of that dedicated RAM.
And does this special RAM area have a name?
It does. This central critical memory area, the main workspace for all crucial database activities, is called the System Global Area, usually shortened to SGA.
SGA, okay.
You can think of it as the database's short-term memory, its active workbench, its brain, if you like, where all the real-time processing, data caching, and manipulation happens at lightning speed. It's absolutely the heart of the database instance.
So the SGA is that 6 GB slice in our example. But how does Oracle know how to divide up that 6 GB internally? Does it just guess when it starts up? Or is there some kind of instruction manual it follows?
Oh, it absolutely does not guess. That would be, well, chaos. No, when an Oracle database instance starts up, the very first thing it does is read a specific file. We call it the P file, which stands for parameter file.
P file. Okay, the parameter file.
Think of this file as Oracle's fundamental instruction manual. It dictates how to configure its memory, its SGA, and various other operational parameters. It's absolutely critical. It tells the database how to behave from the moment it wakes up.
So before Oracle even gets going, before it serves a single query or anything, it checks this blueprint, this P file, to know exactly how much RAM to grab, how to slice it up, and what to do with each piece. That's pretty neat.
It's essential for consistent startup.
And for those listening who might be curious, maybe database administrators, where would you typically find this crucial P file?
Typically, you'll find it in a directory path, something like Oracle Home Database. And the file itself is often named init.ora, where SID is your specific Oracle instance name. So init for initialization, SID for the instance, .ora for Oracle.
And it's sid.ora. Got it.
And inside this text file, you'll find a list of explicit parameters, things that define the various components of the SGA and their sizes. For example, it specifies the DBB block size.
What's that?
That defines the standard size for a chunk of data Oracle works with, maybe 8 kilobytes, for instance. Every piece of data it moves is in these blocks.
Okay.
The P file also defines things like the shared pool size, the size of the log buffer, which is for that redo log buffer we'll talk about, and many other critical memory settings. These parameters dictate exactly how that 6 GB of RAM, in our example, is intricately subdivided and utilized.
So it's the master configuration file for memory.
Primarily, yes. Although, just a quick point for the more experienced listeners out there, while the P file was the original way, in most modern Oracle environments today, you'll actually encounter something called an SPI file.
SPI file. Okay, what's the difference?
It stands for Server Parameter File. It's essentially a binary version of the P file. The big advantage is that it allows administrators to change many of these parameters dynamically while the database is running without needing a full restart.
Oh, wow. That's much more flexible.
Much more flexible, yes. It's stored centrally, usually on shared storage in a cluster. But whether it's the older text-based P file or the newer binary SPFILE, the core concept is identical. These files are the database's startup instructions. They tell it exactly how to set up its memory map, the SGA.
Okay, so we've established the SGA is Oracle's dedicated memory space, configured by the P file or SPFILE. But you mentioned it's not just one big block of RAM, it's intricately divided. Can you give us a quick tour? What are these inner compartments? What's their general purpose?
Absolutely. That total SGA memory, let's stick with our 6 GB example for clarity, isn't one amorphous blob. It's meticulously partitioned into several specialized memory areas. Each one is designed for a very specific job.
What are the main ones?
The key, absolutely mandatory components you always find within the SGA are the buffer cache, which is where the actual data blocks from your tables live temporarily. Then there's the redo log buffer, which is all about recording changes for safety. And the shared pool, which is crucial for processing the SQL statements themselves.
Buffer cache, redo log buffer, shared pool.
Got it.
Mandatory.
Those are the big three you must have. Then there are some other, often optional components like the large pool, the Java pool, and the stream pool, used for more specific tasks. And finally, there's a small but essential area called the fixed SGA.
Okay, lots of tools. And just to reinforce, all of these areas live purely in RAM, right? Not on the hard disk.
Absolutely. Critical distinction. All of these components reside exclusively in that volatile random access memory, the RAM. None of this information we're talking about within the SGA is on the hard disk at this stage of processing.
Yeah.
It's all about speed.
That difference between RAM fast but temporary and the hard disk slower but permanent seems really key here. It kind of reminds me of like writing a document on my computer. When I'm typing, it's all in the computer's RAM,
Yeah.
right? It's volatile.
Mm-hmm.
It's only when I actually hit File Save As that it gets permanently written to the hard disk.
Yeah.
Is that a fair analogy for how Oracle handles data during transactions?
That's an excellent analogy, really accurate. Oracle operates very much like that, and this fundamental design is what allows it to achieve both incredible speed and robust data integrity. Let's trace the journey of data through a typical user transaction to see how it works.
Okay, let's do it.
Imagine you're creating a new sales order in some application. You input the customer details, the items, the quantities. You hit submit or save.
Right.
The data for that specific sales order first generates and temporarily sits in the buffer cache. Remember, that's in RAM.
Okay, data in the buffer cache, RAM.
Almost simultaneously, as that data is being prepared, a corresponding redo entry is generated. This redo entry is basically a detailed sequential log of that specific change you just made, what data changed, how it changed. And that redo entry sits in the redo log buffer, which is also crucially in RAM.
So wait, at this point, both the actual sales order data and a detailed record of the change are just sitting there in volatile RAM. They're not permanent yet.
Correct. They are not permanent yet. They exist only in the fast but temporary memory.
Okay, so when do they actually become persistent? When do they make the jump to the hard disk?
That later is the critical piece of the puzzle, and it involves specific processes we'll get to. But eventually, yes, this information moves from volatile RAM to permanent storage on the hard disk. The actual data blocks from the buffer cache eventually get written out to the data files on the hard disk.
Data files, that's where the actual tables and indexes live permanently.
Exactly. That's your persistent database on disk. And meanwhile, those redo log entries from the redo log buffer make their way to the redo log files on the hard disk. These files act as that unalterable sequential journal of every single change.
So two separate destinations on the hard disk. Data files for the data, redo log files for the change log.
Precisely. This two-pronged approach to persistence, saving the data itself and saving a detailed log of how it changed, is what makes Oracle so incredibly resilient to failures.
Let's drill down into that buffer cache then, because it sounds like the main stage, the central hub where data lives while it's being actively used or changed. What exactly is going on inside there?
It really is the primary staging area. The buffer cache is where actual data blocks, those 8 KB chunks, maybe from your tables and indexes, are loaded from the disk, stored temporarily, and manipulated whenever users or applications access or change them. Think of it as the database's high-speed working memory for data.
And is all the data in there the same, or are there different states?
Good question. Within the buffer cache, data blocks can exist in one of 3 crucial states. It's important to understand these. First, you have free buffers.
Free buffers. Sounds simple enough.
Yep. These are simply empty spaces, unused blocks within the cache, just waiting for data to be read into them from the disk, or maybe waiting for a new transaction to write data into them, just available space.
Okay, empty slots. What's the second state?
Second, there are pinned buffers. Now, this is interesting. A pinned buffer holds data that has been loaded or written into the cache, but the transaction associated with that data is not yet committed.
Not committed, meaning what?
Meaning the user or application hasn't finalized the change. Think about filling out a complex order form online. You filled in some fields, but you haven't clicked Confirm Purchase yet.
Okay, it's in progress.
Exactly, it's in progress. The data related to that transaction might be in a pinned buffer. It's temporarily held or pinned in memory because it's still subject to change, or maybe even a rollback if the user hits cancel or navigates away. The database can't let other processes overwrite it yet because it's not final.
Okay, that makes sense. Free, pinned.
Okay.
What's the third, you said most important, state?
The third and absolutely most critical state for persistence is a dirty buffer.
Dirty buffer. Okay, why dirty?
It's called dirty because the data in this buffer has been modified, and crucially, the transaction that created or modified it has been committed.
Committed. So the user hit confirm purchase, the bank transfer was finalized, the record was saved successfully.
Exactly. This is the final, confirmed, logically complete data resulting from a successful operation. And here is the absolute key insight, the golden rule. Only committed data Only the data residing in those dirty buffers will eventually be written out to the permanent data files on the hard disk.
Why only the dirty ones? Why not the pinned ones too?
Because you wouldn't want to permanently save incomplete transactions, right? Or transactions that a user decided to cancel or roll back. That would lead to data corruption, inconsistencies. It would completely undermine the integrity of your database.
Ah, right. You'd have half-finished orders saved permanently.
Precisely. It's a fundamental principle of any reliable transactional system. Only the confirmed, committed changes are made permanent in the main data store. Dirty buffers represent those confirmed changes waiting to be written.
That distinction makes perfect sense. Only the final confirmed version gets a permanent spot in the data files. So what about the redo log buffer? You called the transaction safety net, and it sounds like its role is absolutely critical, especially for recovery.
Yes, the redo log buffer is, well, it's almost a lifeline for your database. Its sole purpose is to store these things called redo entries.
Redo entries, the logs of the changes.
Exactly. A detailed, sequential, highly accurate record of every single change made to the database in the exact order those changes occur. Think of it as an immutable, real-time journal, or like a detailed transaction receipt for absolutely everything that happens.
What kind of detail are we talking about?
Oh, very detailed. It records things like the before image and the after image of the data blocks that were changed. It records the specific SQL command that was executed. It records who executed it and when. It includes the SCN, that system change number we mentioned.
Wow, okay. Very granular.
Extremely granular, and these entries are absolutely paramount for database recovery. If there's a system failure, power outage, crash, whatever these redo entries, ensure that even if the main data in the dirty buffers hadn't been written to the data files yet, a complete chronological record of all committed changes still exists in the redo logs.
So you can replay the changes.
Precisely. You can replay the log to bring the database back to a consistent state. Without the redo logs, robust, reliable recovery would be simply impossible.
Okay, this sounds like a beautifully choreographed dance between the buffer cache holding the data and the redo log buffer holding the change logs, both in RAM. So who are the dancers? Or maybe the right commanders who actually move this critical data from the volatile RAM down to the permanent hard disk?
That's where two absolutely crucial background processes step onto the stage. They work tirelessly, constantly behind the scenes. These are the DB writer, often abbreviated as DBW, or maybe DBW if there are multiple ones.
DB writer.
And the log writer, universally known as LGWR, pronounced log writer.
DB writer and log writer. DBW and LGWR.
Correct. They are the ones solely responsible for persisting the data from the SGA to the disk files.
And what does each one write? Is it obvious in the names?
It is fairly intuitive, yes. The DB writer, DBW, is tasked with writing the dirty buffers. Remember, that's the committed data from the buffer cache down to the permanent data files on the hard disk.
Okay, DB writer handles the actual committed data blocks.
Right. And the log writer, LGWR, is responsible for writing the redo entries from the redo log buffer down to the sequential redo log files on the hard disk.
Log writer handles the change logs. Okay, that makes sense. DBW writes data, LGWR writes logs. But do they write immediately? Like as soon as a buffer becomes dirty, does DBW write it? As soon as a redo entry appears, does LGWR write it? Or is there some strategy involved?
This is where it gets really interesting. And understanding this difference is absolutely critical for grasping Oracle's robustness and its amazing recovery capabilities. Let's start with DB Writer.
Okay, DB writer, does it write immediately?
No, the DB Writer is not constantly writing data blocks to the data files every time a buffer becomes dirty. That would be incredibly inefficient. Disk I/O is relatively slow compared to memory operations.
Right, constant small writes would thrash the disk.
Exactly. So DB Writer employs a more strategic, often batched approach. It typically waits for specific conditions to be met before it performs a write operation, flushing a group of dirty buffers to disk at once.
Okay, so what are these conditions? What triggers DB writer?
There are typically three main conditions, though the exact behavior can be tuned. First, DB writer often writes when approximately 1/3 of the buffer cache is dirty. So when a certain volume of committed changes is built up, it decides it's efficient to write them out.
1/3 dirty. Okay, what else?
Second, it writes when a checkpoint process initiates it. Checkpoint is another crucial background process we absolutely need to discuss soon. It periodically signals DB writer, essentially saying, okay, it's time to write stuff out, ensuring data gets persisted at regular intervals, guaranteeing a baseline level of permanence.
So checkpoint tells DB writer to write. Got it. And the third trigger?
The third common trigger is when there is no free space left in the buffer cache. If the cache is full of pinned and dirty buffers, and new data needs to be read in from disk, or new transactions are generating data that needs space, DBWriter must write out some of the older dirty buffers to the permanent data files to make room. It has to clear out space.
Okay, so DBWriter is playing a more cautious, optimized game. Waiting for enough data, or a signal from checkpoint, or when it runs out of room, it batches things up.
You could say that, yes, it prioritizes efficiency for data block writes.
So does LogWriter follow the same kind of playbook?
Yeah.
Or is its approach totally different?
Totally, utterly different. And this difference is arguably the linchpin of Oracle's resilience and data safety guarantee. No, the LogWriter, LGWR, is designed for blistering speed and absolute immediate data safety.
Aggressive, you called it earlier.
Extremely aggressive. It writes far, far more frequently than DBWriter. This aggressive logging strategy is Oracle's secret sauce for guaranteeing what we call transactional durability, meaning once a transaction is committed, it's permanent and enabling that rock-solid recovery.
Okay, I'm intrigued. What triggers LogWriter then, if not batching or waiting?
LGWR writes under several conditions, all geared towards getting those redo entries to disk ASAP. First, and most importantly, immediately on commit.
Immediately, like the instant I hit commit.
The instant. As soon as your transaction is successfully committed, its corresponding redo entries are flushed from the redo log buffer to the redo log files on disk. No delay. This is a major reason why committing a transaction often feels instantaneous in a well-tuned Oracle system. The critical record of the change is immediately made permanent on disk.
Wow. Okay, immediate on commit. What else?
Second, it writes every 3 seconds, even if no explicit commit has happened in that interval.
Every 3 seconds. Regardless.
Regardless, if there are any redo entries sitting in the buffer, even from uncommitted transactions perhaps, they get flushed to disk at this frequent, fixed interval. This ensures that even if the system crashes between commits, very little potential redo information is ever lost from volatile memory.
Okay, that's frequent. Any other triggers?
Yes, a third key point is related to DBWriter. LGWR often writes to disk before DBWriter gets around to writing the actual data blocks. In fact, there are mechanisms ensuring that redo information for a change is always on disk before the corresponding data block change is written to the data file.
Always. The log always hits the disk before the data.
Yes. This is a fundamental principle called write-ahead logging. It makes the redo logs the very first permanent record of any changes in your database. It safeguards the recipe for recovery even before the meal, the actual data blocks, is permanently stored.
Okay, now that feels like a truly profound insight. The log is always ahead of the data on disk. Why does that difference in aggressiveness, that write-ahead logging, matter so much for something as critical as data recovery? Can you walk us through a scenario, maybe a dramatic one, to really hammer this home?
Let's absolutely do that, because seeing it in action makes the design choice crystal clear. Imagine you've just successfully executed and committed 10 really critical transactions. Maybe they're 10 vital sales orders, back to back.
Okay, 10 committed orders.
Oracle assigns each committed transaction a unique sequential identifier. We mentioned these before. System change numbers, or SCNs. Think of them like global version numbers or precise timestamps for the entire database state. So let's say your 10 transactions correspond to SCNs 100 through 110.
SCN 100, 101, 102, up to 110. Got it.
Now, because LogWriter is so aggressive and writes immediately on commit, as each of those transactions, 100, 101, etc., is committed, its redo entries are immediately, definitively, and permanently written out to your redo log files on disk. They are safely stored there, sequentially, done, secure.
So the log files on disk have the record of changes up to SCN 110 instantly.
Correct. However, the actual data for these transactions, currently sitting as dirty buffers in the buffer cache in RAM, the stuff that will eventually populate your data files on disk, might not have been written to those data files yet.
Why not?
Because remember, DBWriter is waiting. Maybe less than 1/3 of the buffer cache is dirty. Maybe a checkpoint hasn't happened yet. Maybe there's still plenty of free space in the cache. So DBWriter is patiently waiting to batch more operations for efficiency.
Okay. So the redo log files on disk are fully up to date with SCN 110. But the physical data files on disk might only contain committed data reflecting the state up to, say, SCN 99 from earlier transactions.
Precisely. The logs are ahead of the actual data files. The recipe is permanently saved on disk, but the cooked meal isn't fully updated on disk yet. It exists only in RAM for SCNs 100, 110.
Okay, I can see where this is going. What happens if disaster strikes right at this exact moment?
Now, imagine the absolute worst-case scenario. Bam! Sudden power failure, hardware crash, server just dies unexpectedly. Right now.
Oh,
Remember, RAM is volatile memory. Everything in it disappears when the power goes off. So all that unwritten data in the buffer cache, including the data for your critical transactions, SCN 100 through 110, which were committed but not yet flushed to the data files by DB writer, is instantly, irretrievably lost from memory. Poof.
God.
Gone from RAM, and your data files on disk. They still only reflect the state of the database up to SCN 99. It looks like those last 10 transactions never happened if you just look at the data files. Panic time, right? Looks like data loss.
Yeah, that sounds like panic time. My 10 critical orders are gone.
But here's the brilliance. Here's the genius of Oracle's design, thanks to the aggressive log writer. Oracle doesn't panic, because your redo log files, safely stored on disk, contain all the changes precisely and sequentially right up to SCN 110.
Ah, the recipe is still there.
The recipe is perfectly preserved on disk. So when the system restarts after the power comes back, Oracle leverages its robust automatic recovery mechanisms. This is primarily driven by the System Monitor Process, SMON, which we'll discuss next.
Okay, SNON kicks in.
Yes, SMON automatically detects that the database didn't shut down cleanly. It consults the control file and the data file headers, sees they're not synchronized with the latest logs, and then it meticulously reads through those redo log files. It finds the records for SCN 100, 101, 102, all the way to 110, and it applies those changes to the data files. It essentially replays the committed transactions that were lost from memory.
It rolls forward. It uses the log to rebuild the missing data in the data files.
Exactly. It rolls forward all committed transactions recorded in the redo logs that hadn't made it to the data files before the crash. This brings your database completely and consistently up to date, right to the point of the last committed transaction, SCN 110, before the failure. Your 10 critical orders are safe and sound. No committed data is lost.
Wow, that is genuinely impressive.
Isn't it? This profound difference in how log writer, fast, aggressive, commit-focused, and DB writer, slower, batched, efficiency-focused, operate, combined with that write-ahead logging principle, is absolutely foundational to Oracle's industry-leading, robust recovery capabilities. It's the core reason why your committed data is safe, even if the system crashes catastrophically mid-operation. The redo logs truly are the unsung heroes of database resilience.
They capture every change immediately, ensuring that no matter what happens, Oracle has that complete chronological journal to reconstruct your data perfectly.
Exactly. This aggressive logging means that even if the primary data blocks aren't yet permanently written to disk, the recipe for recreating them is, making loss of committed data incredibly rare, practically unheard of, in a properly configured Oracle database.
That recovery mechanism is seriously cool. A real testament to some clever, maybe slightly paranoid engineering. It sounds like a lot of the SGA we've discussed, buffer cache, redo log buffer, is heavily focused on storing data and ensuring its safety through logging. But what about processing? What about handling all those complex SQL statements efficiently, making sure queries run fast?
Yes, performance. That brings us to another absolute cornerstone of the SGA, one that's arguably just as critical for everyday user experience. The shared pool.
Shared pool. Okay, what is its main job?
The shared pool is primarily where Oracle handles the complex task of parsing SQL statements. It's an absolutely critical area for optimizing database performance, especially when you have many users running similar queries.
Parsing. What exactly does that entail? Is it just like checking the SQL for typos, like spell check for code?
It's much more involved than just proofreading, although that's part of it. Parsing is a rigorous, usually two-step verification and preparation process that happens every time a new or unseen SQL statement is submitted to the database.
2 steps. What are they?
First, there's a syntax check. This is where Oracle verifies if the SQL statement is structurally correct. Does it follow the grammatical rules of the SQL language? For example, select column 1, column 2 from employees where department to dig list 10 is syntactically correct. But something like select from employees where department to dig list 10 is wrong because it's missing the column list after select.
Okay, so step 1 is grammar check. Makes sense for a structured query language.
Precisely. Structure is key. Second, and equally important, there's a semantic check. This goes beyond grammar. Here, Oracle checks if the statement actually makes sense in the context of your specific database schema.
What does that mean?
It checks things like, do the tables and columns mentioned in the query, employees, column 1, departmented, actually exist in the database? Does the user who submitted the query have the necessary permissions or privileges to access that table and those columns? It's about meaning, context, existence, and security, not just the structure of the command.
Ah, I see. So syntax is the sentence formed correctly, and semantics is, does the sentence actually mean something valid in this specific database?
Excellent way to put it, yes.
So the shared pool is where these syntax and semantic checks happen. Once Oracle has done all that work, what does the shared pool actually contain? Where does it store the results of this parsing effort?
Good question. After a SQL statement is successfully parsed, passes both syntax and semantic checks, Oracle doesn't just throw that work away, it also generates an optimized execution plan for that SQL statement, basically. The best strategy Oracle figures out for actually retrieving the requested data efficiently, like which indexes to use, how to join tables, etc.
Okay, so it parses and plans the execution.
Right. And the shared pool then contains two key internal caches, specifically designed for storing this parsed SQL data and its associated execution plan, primarily to enable reuse and boost performance. The first, and arguably most important for user queries, is the library cache.
Library cache, what does it store?
The library cache stores the parsing results, the syntax check outcome, the semantic check outcome, and crucially, the optimized execution plan for SQL statements executed by users and applications. So every time you or your application runs a query, if it's new, its parsed form and plan gets stored in the library cache.
Okay, and the second cache within the shared pool?
The second one is the dictionary cache, which is also sometimes known as the row cache. This cache stores similar parsing and metadata information, but specifically for SQL statements executed internally by the Oracle system itself.
Oracle runs its own SQL.
Constantly. For instance, when Oracle needs to look up table definitions, column data types, user privileges, storage parameters, or other critical metadata information from its internal data dictionary tables, which are just special Oracle tables themselves, it uses its own internal SQL queries to retrieve that info. The parsed results of those internal queries reside in the dictionary cache, speeding up Oracle's own internal operations.
Okay, library cache for user SQL, dictionary cache for Oracle's internal SQL. Now, how does this shared pool mechanism directly impact performance? Because this is where it gets really interesting for me, and probably for anyone who's ever waited for a query to finish. How does this translate to real-world speed?
This is where the shared pool becomes an incredibly powerful performance optimizer. It all hinges on reuse. If your shared pool is generously sized, meaning you've allocated enough RAM to it in your P file or SPF file configuration, it can hold on to a much larger number of these parsed SQL statements and their execution plans in the library cache.
More space means it can remember more past queries.
Exactly. Now, here's the magic. What happens when a user or an application executes the exact same SQL statement again? Maybe a common report query or frequent lookup.
Does it have to parse it all over again? Syntax check, semantic check, build a plan?
No. That's the beauty of it. If the shared pool is well-sized and the statement is still in the library cache, Oracle recognizes it's seen this exact SQL before. It doesn't need to reparse it from scratch. Instead, it performs what's called a soft parse.
Soft parse, as opposed to
a hard parse, which is the full, expensive process of syntax check, semantic check, and optimization we just described. A soft parse is much, much faster. Oracle simply retrieves the already validated, already optimized data and execution plan directly from the library cache.
So if I ask Oracle the exact same question repeatedly, it doesn't have to think about it from scratch every single time. It's like having a really good instant memory for conversations or tasks you've already done perfectly before. That sounds like a huge time saver.
It is a massive time saver. This reuse significantly reduces the time taken for those computationally intensive syntax and semantic checks, and crucially, avoids the complex process of generating a new execution plan. Both of those consume significant CPU cycles.
So less CPU work, faster response time.
Precisely. It transforms what would be an expensive hard parse into a very lightweight soft parse. The direct result is much faster query execution, a noticeable reduction in overall CPU usage on the database server, and consequently a significant improvement in overall database performance, responsiveness, and scalability, especially under heavy load.
Wow.
It's a classic, brilliant example of intelligent caching in action, optimizing access to frequently needed information, in this case parsed SQL plans, to dramatically speed up future requests. The more repetitive your application's SQL queries are, the greater the benefit you'll see from a well-sized shared pool. Database administrators often monitor something called the library cache hit ratio.
Hit ratio?
Yeah, it measures how often Oracle finds a needed SQL statement already parsed in the cache, a hit, versus having to do a hard parse, a miss. A high hit ratio, ideally well above 90% or even 95%, indicates efficient reuse and good performance.
And a low hit ratio means?
A low hit ratio suggests the shared pool might be too small, or maybe the application is generating lots of unique, non-reusable SQL statements. This leads to constant hard parsing, high CPU consumption, and often frustratingly slow application performance. This is also a key reason why database developers are strongly encouraged to use something called bind variables in their application code.
Bind variables, what do they do?
Bind variables are essentially placeholders in SQL statements. Instead of writing select from orders where ordered in L23 and then select from orders where ordered in 2456, you write select from orders where ordered equals .order placeholder, and then you just supply the value 123 or 456 separately. This allows Oracle to see that the underlying SQL statement structure is identical, even though the specific value changes. It enables Oracle to reuse the parsed plan from the library cache much more effectively, dramatically improving the hit ratio and performance for applications that execute similar queries with different data values. Not using bind variables is a very common cause of performance problems related to shared pool contention.
Okay, that shared pool and its caching mechanism for SQL is clearly vital for performance. Now, besides the buffer cache, redo log buffer, and shared pool, you mentioned some other more specialized pools within the SGA earlier. Large pool, Java pool, screen pool. What are those used for? Why do they sometimes get their own dedicated space instead of just using the shared pool?
Right. These are designed to handle specific, often memory-intensive functionalities without disrupting the critical work happening in the shared pool, especially the library cache. If these operations use the shared pool heavily, they could potentially push out those valuable parsed SQL statements, hurting general query performance. So giving them their own space can be beneficial.
Makes sense. Keep the specialized heavy lifting separate. So the large pool, what's its job?
The large pool is primarily used for a few specific things. One major use is for session memory in a shared server configuration, formerly known as multi-threaded server, or MTS, where many user connections share a smaller number of server processes. It's also heavily used for the execution of certain types of PL SQL statements, especially those dealing with large objects or collections.
PL's code, that's Oracle's own programming language extension, right?
Exactly. Oracle's procedural extension to SQL, allowing for more complex, stored program logic like procedures, functions, and packages. Certain parallel query execution operations also leverage the large pool for message buffers between parallel processes. And importantly, Oracle's Recovery Manager tool, RMNN, often uses the large pool for its backup and restore operations, especially for buffering I/O. These tasks can require significant chunks of contiguous memory, which the large pool is designed to provide without fragmenting the main shared pool.
Okay, large pool for shared server sessions, some PL SQL, parallel queries, and RMN backups. What about the Java pool? That sounds pretty self-explanatory.
It is, mostly. The Java pool is used specifically when your Oracle database runs Java code or stores Java objects directly within the database. Oracle has a built-in Java virtual machine, JVM. Remember, Oracle actually acquired Java from Sun Microsystems many years ago and has deeply integrated Java capabilities into the database platform. So if you're running Java stored procedures or using other Java features inside Oracle, the Java pool provides the necessary memory heap for that embedded JVM.
Right, Oracle owns Java. Makes sense they'd have a dedicated pool for it. And the last one you mentioned was the stream pool. What kind of streams are we talking about?
The stream pool is dedicated specifically to Oracle's data replication technologies. Primarily, this means Oracle Streams, an older technology, and its successor, Oracle Golden Gate, which is now the strategic solution.
Data replication, like copying data from one database to another.
Exactly. For things like creating logical standby databases for disaster recovery, feeding data warehouses, or enabling real-time reporting from a separate database instance. When replicating data, changes captured from the source database are often processed and buffered in the source database's stream pool before being sent across the network. Then, on the target database, the incoming changes might be buffered in its stream pool before being applied to its physical files. It facilitates efficient, high-volume, often real-time data transfer and synchronization between databases.
Okay, so large Java and stream pools handle specific, heavy-duty, or specialized tasks. What about that small, almost mysterious fixed SGA you mentioned earlier? It sounds different from the others. What does it actually do?
Yeah, the fixed SGA is a bit different. It's a relatively small internal area within the SGA whose size is generally fixed at database startup and doesn't change much. Its purpose isn't really user data or SQL parsing, but rather holding internal housekeeping information about the state of the database and the instance itself.
Housekeeping, like what?
It contains critical internal control structures, things like database state information, instance status, internal latches and locks that manage concurrency between background processes accessing shared memory structures, pointers to the other SGA components, like where the buffer cache starts, where the shared pool starts, process state information, and so on. Think of it as the SGA's internal administrator or metadata repository. It holds information about all the other memory areas and the instance's operational status, ensuring everything is properly organized and accessible by the background processes. It's less about the user's data and more about the database's own internal bookkeeping and control mechanisms.
So we have all these components within the SGA, the big mandatory ones like buffer cache, redo, log buffer, shared pool, fixed SGA, and then the optional specialized ones like large Java and stream pools. Is that mandatory versus optional distinction important? Do you have to define all of them?
That's a very important distinction, yes. It really speaks to Oracle's design philosophy of balancing essential core functionality with flexibility for different workloads. There are absolutely mandatory components of the SGA. These must be defined with some size, even if it's implicitly calculated, in your P file or SPF ILE when you create or start the database.
And those mandatory ones, again, are?
The buffer cache for data, the redo log buffer for change logging, the shared pool for SQL parsing and more, and the fixed SGA for internal control. These four are absolutely fundamental to core database operation. You simply cannot run an Oracle database without them. There'd be no way to handle data blocks, log changes, process SQL commands, or manage the database's internal structure. An Oracle instance literally cannot start if these aren't configured.
Okay, those four are non-negotiable. So what happens if I don't explicitly configure or define sizes for the large pool, Java pool, or stream pool in my parameter file? Does the database just fail to start or refuse to do PL SQL or Java or replication?
No, that's where Oracle provides significant flexibility. The large pool, Java pool, and stream pool are considered optional components. If you don't explicitly define specific sizes for them in your P file or SPF ILE, or if you set their size to 0, Oracle won't just fail. Instead, it will attempt to automatically allocate memory for those functions dynamically from the shared pool as needed.
So the shared pool acts as a fallback or a general reserve if the specialized pools aren't defined.
Exactly. The shared pool can serve multiple purposes, while this offers flexibility, meaning the database will still function, and you can still run PL SQL or Java or use streams to some extent. Relying on the shared pool for these potentially memory-hungry operations isn't always optimal for performance.
Why not? What's the downside?
The main downside is contention and potential fragmentation within the shared pool. If large RMN backups or complex parallel queries or lots of Java activity start allocating big chunks of memory from the shared pool, they can push out those valuable, frequently used parsed SQL statements from the library cache. This forces more hard parses for regular user queries, hurting overall performance. It can also make the shared pool's memory management more complex.
So while it works, it might slow down my normal SQL queries if the shared pool gets too busy with these other tasks.
Precisely. That's why, for optimal performance in environments that rely heavily on large PL SQL operations, Java within the database, shared server configurations, or extensive data replication, explicitly configuring dedicated, adequately sized, large Java or stream pools is highly recommended. It isolates those workloads and protects the performance of your core SQL processing in the shared pool.
That makes total sense. Isolate the noisy neighbors.
Kind of like that, yes. This whole hierarchy of mandatory components, ensuring the basics always work, and optional dedicated components, allowing optimization for specific needs, really highlights Oracle's core design principles. They ensure fundamental operations are always resourced and reliable, while simultaneously offering administrators the flexibility to fine-tune the system and dedicate resources for specialized workloads when needed, allowing them to tailor the instance to their specific application demands.
Okay, we've spent a good amount of time digging into the SGA. Oracle's incredibly clever, complex use of memory, that fast, volatile RAM where all the immediate action happens, caching data, logging changes, parsing SQL. But, memory by itself isn't enough to actually bring a database to life, is it? Like, I can have a Word document file sitting on my hard drive, but I can't really do anything with it. I can't edit it. I can't even properly read its content without running the Microsoft Word application.
Precisely. That's the perfect segue. Memory structures are just one half of the equation. This brings us to the second, equally vital half of the Oracle architecture puzzle, the Oracle instance.
The instance. We've used that term a few times. What is the core definition of an Oracle instance?
The simplest definition is this. An Oracle instance is the combination of the allocated RAM memory structures, primarily the SGA that we've just explored in detail, plus a set of critical background processes that continuously run and actively manage the database.
SGA plus background processes equals instance.
Exactly. Let's use another analogy. Think about playing a video file on your computer. You have the video file itself, like the data files on disk, but to watch it, you need an application, say, VLC Player. When you launch VLC, two things happen. Some memory is allocated for the player itself to buffer video frames and run its code, like the SGA. And a process, maybe VLC.exe on Windows, starts running in the background to actually decode the video data, handle audio, display the picture, respond to your clicks, like the background process of it.
Okay, so the running VLC application is the VLC instance, memory plus the active process.
Precisely. It's that active running entity that makes the inert file usable. It's exactly the same with Oracle. You can't just look at the .dbf data files sitting on your disk and understand them or interact with them in any meaningful way. You absolutely need the active Oracle instance, that combination of the SGA memory structures and the running background processes to interpret that data, allow connections, process queries, enforce rules, and manage everything.
So it's like my .doc file analogy. I can see the file icon, but I can't read the words or change the formatting without the MS Word instance running. The files are just inert data until the instance software brings them to life.
Perfectly put. Without the Oracle instance running, meaning specifically both the SGA memory allocated and those critical background processes started and active, you simply cannot access, read, or modify your Oracle tables or the table spaces where they reside. The data files are just a collection of bits and bytes on disk, fundamentally unreadable and inaccessible in a structured way until the instance wakes up, reads them, interprets them, and provides all the mechanisms to interact with and secure that information. It's the instance that allows users like you to connect, run SQL, get data back, save changes, and ensures all the complex rules and integrity constraints of the database are constantly enforced.
Okay, so the instance is SGA plus processes. We've covered the SGA. What are these critical background processes then? The second half of the instance equation. We know systems like SAP have their own processes, dialog, background, update, etc. What are the core, absolutely mandatory processes that make Oracle function as a robust database? The ones that have to be running.
Oracle has its own set of absolutely essential mandatory background processes. These are the real unsung heroes, working continuously, tirelessly, 204/7 behind the scenes, ensuring data integrity, performance, consistency, and recoverability. There are 5 main ones that are considered mandatory for almost any standard Oracle instance to function, and we've actually already hinted at or even named a couple of them.
Okay, the famous 5 of Oracle processes. Let's meet them. Who's first?
First up, we have the checkpoint CKPT process.
Checkpoint, CKPT. We mentioned this one triggers DB Writer.
Exactly. That's its first crucial duty we discussed. CKPT's primary role in coordination with DB Writer is to ensure that committed data eventually gets written from the buffer cache to the data files on disk. It periodically signals DB Writer, basically saying, okay, sync up. Write out dirty buffers up to this point. This isn't just a casual save reminder. It's a critical synchronization event that establishes a point of consistency between memory and disk.
So it's coordinating the saving of data. But you said it does more. It's about synchronizing everything.
Yeah, precisely. It has other vital synchronization duties. Its second crucial job is to update the headers of all the data files with the latest system change number, SCN, associated with that checkpoint event. Remember, SCNs are those global version numbers. Writing the SCN to the data file headers ensures that Oracle knows, just by looking at the file, how up-to-date it is relative to the logs and the overall database state. This is vital for recovery coordination.
Okay, updates data file headers with the SCN. What else?
And third, Checkpoint continuously writes critical synchronization information, including the current SCN, and information about which redo log file is currently being written to, the log sequence number, to the control file.
The control file, you mentioned that's like the database's master map.
Exactly. The control file is a small but absolutely vital binary file. Usually Oracle keeps multiple copies for safety that contains the names, locations, and status of all the physical database files. Data files, redo log files, archived log files if used. It also holds critical metadata like the database name and the SCN information needed to ensure all these files are consistent and synchronized during startup and recovery. Checkpoint keeps this master map constantly updated.
Wow. So if Checkpoint isn't running or fails?
Disaster. If Checkpoint isn't running correctly, Data files don't get updated consistently, their headers don't reflect the true state, the control file loses synchronization. Recovery from any kind of failure becomes incredibly difficult, probably impossible without significant data loss. CKPT is fundamentally critical for database consistency, durability, and efficient recovery. It ensures there are known points in time where memory and disk were synchronized.
Okay, Checkpoint sounds like an incredibly important workload orchestrator and consistency manager, keeping memory, data files, and the control file all in sync. Whew, what's the next mandatory process in this unseen workforce?
The second mandatory process is the system monitor, universally known as SMON.
SMON, System Monitor. What's its job? Is it just watching things?
It does monitor, but its primary and perhaps most critical active job is automatic instance recovery. Remember our power failure scenario.
That's where the log saved us.
SMON is the process that actually performs that recovery when the instance starts up after a crash. It automatically detects that the previous shutdown wasn't clean. We call this instance recovery. It then reads the redo log files, identifies the committed transactions that were lost from the SGA buffers, and applies those changes, rolls them forward to the data files, bringing the database back to a transactionally consistent state right up to the point of failure.
So SMON is the database's built-in paramedic, the emergency responder that uses the logs to fix things after a crash.
That's a great way to think about it. It's Oracle's self-healing mechanism for instance crashes. SMON also performs other essential background cleanup duties during normal operation, like coalescing free space and table spaces, or cleaning up temporary segments that are no longer needed after certain operations fail or complete. It's the janitor, too, in some ways, but its key role is that automatic recovery.
Okay, SMON is the auto healer and cleaner. Fantastic. We have Checkpoint, CKPT, System Monitor, SMON. We know DB Writer, DBWn, Log Writer, LGWR are implicitly mandatory because checkpoint and recovery depend on them. That's 4. Who's the 5th mandatory process?
The 5th, and in many ways the most foundational, is the process monitor, known as PMON.
PMON, process monitor. What does it monitor? The other processes.
Exactly. PMON is, in a very real sense, the ultimate overseer. It's the leader or parent for all other Oracle background processes within the instance. In fact, when you start an Oracle instance, PMON is typically the very first background process to come alive. And its primary responsibility is then to start up, manage, and continuously monitor the health and status of all the other mandatory background processes we've discussed: DB Writer, Log Writer, Checkpoint, and SMON.
So PMON is the manager, the supervisor, the central authority keeping an eye on the critical workforce.
Precisely. It's constantly checking. Is DBW running? Is LGWR okay? Is CKPT doing its job? Is SMON active?
Okay, but what happens if PMON detects a problem? What if one of its critical subordinates, say LogWriter or LGWR, suddenly fails or crashes unexpectedly? Does PMON try to restart it? Or what?
Here's where PMON demonstrates its strictness and Oracle's unwavering commitment to data integrity above almost everything else. If PMON detects that any of the other mandatory background processes, DBW, LGWR, CKPT, SMON, have died or failed unexpectedly, PMON does not try to restart just that one process. Instead, PMON will immediately and deliberately crash the entire Oracle instance.
Wait, really? It crashes the whole database if just one of those background processes fails? That sounds drastic. Why not just try to fix the broken part? Isn't uptime important?
It sounds drastic, and yes, uptime is hugely important, but there's a profoundly critical reason behind this seemingly extreme design choice. Think about what those processes do. DB Writer persists committed data. Log Writer persists the recovery logs. Checkpoint synchronizes everything. SMO handles recovery. These processes are so absolutely fundamental to maintaining data integrity, consistency, and the ability to recover reliably that operating the database without one of them, even for a short time, would introduce an unacceptable risk.
What kind of risk?
The risk of severe data corruption, irreversible data loss, ending up with a database in an inconsistent state from which you might never be able to recover properly. Imagine running without LGWR commits might happen, but the redo log isn't being written. If you crash then, recovery is impossible. Imagine running without DBW for too long, the buffer cache fills up, performance tanks, and a crash could lose vast amounts of committed data.
Okay, I see. The risk of continuing without a critical component is actually worse than the disruption of a controlled shutdown.
Exactly. PMON acts as the ultimate failsafe. It prioritizes the absolute integrity and recoverability of your data above continuous uptime when a critical internal component fails. It decides that the consequence of limping along with a broken core process would likely be far worse for your precious data than initiating a controlled, immediate instance termination. This allows SMON to perform a clean instance recovery when it restarts, using the logs that were successfully written up to the point of the failure. PMON is truly the ultimate guardian in that sense. It has zero tolerance for critical failures in its essential subordinates. It's a fascinating philosophical choice in database design, isn't it? Oracle explicitly chooses to prioritize immediate data integrity and the guarantee of full recovery over attempting continuous uptime at all costs when core safety mechanisms are compromised. It's a powerful testament to Oracle's unwavering commitment to data reliability, which is absolutely paramount in the enterprise systems where it typically operates.
That is a powerful and maybe even somewhat uncompromising design choice. Better to go down safely and know you can recover perfectly than to risk corrupting valuable data by trying to keep running with a critical flaw. That makes a lot of sense when you put it that way. So just to recap this crucial section on processes, these 5 DB writer, DBW, log writer, LGWR, checkpoint CKPT, system monitor, SMON, and process monitor, PMON, are the absolutely mandatory background processes for a standard Oracle database instance. They work tirelessly in concert with the SGA memory structures to make the database functional, performant, consistent, and perhaps most importantly, completely recoverable. They are the essential workforce of the Oracle instance.
Absolutely. Those 5 form the core. And while they are the mandatory foundation, it's worth just briefly mentioning again that Oracle often employs other important background processes too, depending on your specific configuration and the features you're using. These aren't strictly mandatory for the instance to just start, but they are often vital for specific functionalities.
Like which ones?
Well, for instance, the ARCH archiver process. If you run your database in what's called archive log mode, which is essential for point-in-time recovery and robust backup strategies, the ARCH process is responsible for automatically copying the online redo log files to a separate archive log destination before LGWR overwrites them. This preserves a complete history of all changes, allowing you to recover the database to any specific moment in the past. ARCH is crucial for serious production environments.
Okay, ARCH for saving old logs.
Yeah.
Any others?
There's the Arikeo recover process, which is used in distributed database environments to automatically resolve failures in transactions that span across multiple databases, ensuring consistency across systems. In highly available environments using Oracle Real Application Clusters, RAC, where multiple instances share the same database, you'll also see critical LCKX lock processes managing the complex inter-instance locking needed to ensure data consistency when multiple instances might try to access the same data block.
REC adds more complexity, more processes.
Definitely. And for systems supporting a very large number of concurrent users, you might configure shared server mode, which uses DShtag tag dispatcher processes to funnel many user connections through a smaller number of shared server processes, conserving memory resources. These dispatchers manage the user connection queue.
Dispatchers for connection pooling.
Right. So while the core 5, PMON, SMON, CKPT, DBW, LGWR, are mandatory for basic function, these others like RCH, RECO, LCKX, dispatchers, and several more play vital roles depending on the specific features and configuration you've enabled. Each contributes to the database's overall robustness, scalability, availability, and efficiency. They are part of that larger, unseen workforce making Oracle tick. #outro.
Wow. We have covered a tremendous amount of ground today. We've really peeled back the layers of Oracle's inner workings, haven't we? From the highest level, how it shares memory on a server, down to the intricate details of the system global area, SGA, and its specialized pools like the buffer cache, the redo log buffer, the shared pool.
We saw how the buffer cache holds data in different states, free, pin, dirty, and how only committed dirty data gets written eventually.
And how the redo log buffer acts as that critical safety net, capturing every single change.
Driven by that aggressive log writer process, LGWR.
Right, compared to the more measured DB writer, DBW, that difference being key to Oracle's amazing recovery capability.
Absolutely. And then the shared pool acting like the database's memory for SQL statements, using the library cache to avoid costly reparsing through soft parses.
Plus, those vital background processes, checkpoint keeping everything synchronized, SMON performing automatic recovery, and the ultimate guardian, PMON, overseeing them all and ensuring integrity even if it means shutting down.
It's a complex, but remarkably coherent and robust system when you see how the pieces fit together.
It really is. And that combination, that synergy between the intelligently allocated RAM memory in the SGA And these essential, tireless background processes, that is what we call an Oracle instance.
The living, breathing entity that makes your database accessible and usable.
Exactly. The instance is what truly allows you, or your applications, to interact with those inert data files on the hard disk, to send queries, to get results, to make changes, to make sense of the vast amounts of information stored there. Without that instance running, your data files are just, well, they're just a static collection of bits, like a bookshelf filled with books welded shut. Useless until the instance opens them.
Good analogy. The instance brings the data to life.
So now, hopefully, when you hear discussions about database performance tuning or the absolute necessity of database backups and recovery strategies, or even just wonder why your online banking transaction felt so instantaneous and secure, you have a much clearer, much more informed picture. You can visualize that intricate, coordinated dance happening constantly beneath the surface.
It really is a testament to decades of sophisticated engineering, all designed with two primary goals in mind. Keep your data access fast, and keep your data absolutely safe and consistent, often in mission-critical environments where downtime or data loss simply isn't an acceptable option.
Which leads to maybe a final thought to ponder. Considering how meticulously, how aggressively Oracle logs every single change, using LGWR and the redo logs specifically to ensure robust recovery, make you absolutely certain that even a catastrophic power outage doesn't mean losing committed transactions. What does that intense focus on logging tell us about the fundamental, perhaps almost incalculable, value we place on every single transaction in our modern, interconnected, data-driven world?
That's a deep question.
Think about it. How many actions you take every day, sending a critical email or text, making a payment, updating a patient record, booking a seat, rely entirely on complex systems that deep down prioritize this kind of robust, immediate, persistent logging to guarantee data integrity above almost all else. What other hidden safety nets, similar to Oracle's redo logs, might be absolutely crucial in our digital lives, operating silently in the background, that we never even think about, yet depend on completely for the seamless, reliable functioning of our society?
It makes you realize how much trust we place in these underlying mechanisms.
It really does. Okay, that's it for this deep dive into Oracle's memory and processes. We hope you gained some surprising, maybe some truly valuable insights into this hidden world that powers so much of our lives.
Hopefully it demystified some of the magic.
Join us next time for another deep dive into a fascinating topic that will, we hope, leave you well informed and just as curious.